So welcome to the Winds and Currents webinar. Today we have Hector Torres, who's going to talk about advancing knowledge of cross-scale ocean current interactions using the ODYSEA wind and current mission concept. So I'll let you take it away, Hector. Thank you for doing this.
Thanks, Sarah. So this is a talk that I was supposed to give 1 month ago. Unfortunately, I was doing some Doppler tasks. But so the idea today is to highlight the advantages of having a satellite mission like ODYSEA, in the sense that what are how we can exploit the wide swath, the temporal sampling, which is going to, in some places, is twice a day, and also the high resolution of surface currents, in the estimation of the interactions across the scales. And so this is the team at GPL, and most of the talk is I have feedbacks from them. And so let's see. So back in the days, topics Poseidon was a huge technological advance, in the sense that for the first time we have picture of the turbulent nature of the ocean. And what we found is that, well, it was more turbulent than we expected, in terms of the mesoscaletes interacting each other's with each of mesoscaletes with different sizes. And yeah, but however, this type of observation has limitations in terms of spatial resolution and temporal sampling. Although, in fact, we have we were able to understand quite a bit of how the ocean interact, how the oceanic motions interact each other. And one of the metrics we used is the famous nonlinear kinetic energy fluxes plotted in the spectral space, in the web number space. So so here's the definition of the kinetic energy fluxes. It's just the integral of the nonlinear term of the kinetic energy equation across web numbers. And so this is the information that we can get from this type of analysis. And here I will emphasize the several scales associated to this, to the kinetic energy fluxes. The first one is the inverse kinetic energy cascade, which is emphasized by the minimum relative in the negative side, and also we call it the inverse cascade, and the forward kinetic energy cascade, which is in the positive side. Also, there is this energy injection scale, which is associated to the close to the Rossby radius of the formation. So these are three scales that are three spatial scales that are important in order to understand how the ocean and how the oceanic motions interact. So the idea is, okay, we have information from the conventional altimeters. So now, how we can what is how we can extend this knowledge using ODYSEA? Can we retrieve the dual kinetic energy cascade? So when I say dual kinetic energy cascade, it means that we can capture the inverse, but also the forward energy cascade. So in 2005, Robert Scott and Wang, they use conventional altimeters to retrieve to estimate the nonlinear kinetic energy fluxes, and they were able to identify the inverse kinetic energy cascades, but also the direct kinetic energy cascade. So here we have to keep in mind that the resolution, the effective resolution of conventional altimeters is 70 kilometers. So maybe well, now we know that the direct cascade that Scott and Wang found was underestimated. But yeah, they were able to find the inverse kinetic energy cascade, and here and after there were an explosion of numerical simulations that allow us to either confirm or infirm this the dual kinetic energy cascade. And one of the studies that I liked is the one done by Brian Arvin in 2013. So he used a numerical simulation, and also he compared this kinetic energy cascade estimated from numerical models against Aviso data. But also he played with the temporal sampling. No, sorry, the temporal resolution and the spatial resolution. So here, for instance, he showed the kinetic energy fluxes in two regions, the Gulf Stream and the Kuroshio. So the black line is the fluxes computed from the numerical simulation without any spatial filter or temporal filter. And as you can see, this huge inverse kinetic energy cascade, and also the direct cascade, but is now the inflection point, the injection scale is not at 150 kilometers, is put at higher web numbers. I think I don't quite remember the particular scale that he found, but here the point is that the inverse kinetic energy cascade was stronger than the one computed from Aviso data, where is represented by this cyan line here. So this is the cyan line is what is called in one found in 2005. So here's the inverse cascade, although it's underestimated, but the direct cascade is overestimated in the Aviso data. Why? Because, well, the resolution, spatial resolution to the temporal sampling. So they are missing. So here the main point is that the Aviso data is missing the small scales. And this information was further confirmed later on by numerical simulation with more higher resolution.
Hector, mind if I jump in for just a second on that last slide? So what I also found is that if you filter the model in space and time in a manner similar to the construction of the Aviso product, then you get that green curve, which looks a lot like the Aviso curve. So it's just telling you, if you take the model as truth and you filter it, then you get something that looks like what you get from Aviso. So yeah.
So it means just to emphasize the impact of the smaller scales and high frequency motions on the kinetic energy fluxes. Yeah, thanks, Brian. And so in Sasaki et al. In 2014, now with this bigger numerical simulation with more spatial resolution and temporal and model outputs. So what they found is, well, this kinetic energy cascade also experience a seasonality. It's not the same if you are during the winter against the summer. And also what they found is that, well, the direct cascade, the injection scale can go down to between 20 and 30 kilometers. Well, of course, this also will depend on the spatial resolution of the model. But here, one of the information that I would like to emphasize is the seasonality. So in the summer, it's mostly you find the inverse cascade. But in the winter, so we have this explosion of submesoscales, and we have this intense direct energy cascades, and at a small scale. So with ODYSEA, the idea is, I think, when it's in the proposal, the idea is, well, is ODYSEA capable of capturing this seasonality? The seasonality associated to the kinetic energy fluxes, plus is ODYSEA capable of capturing the dual kinetic energy cascade? Again, is whether ODYSEA is able to capture an inverse cascade as well the direct cascade, and the injection scale is located at the right position. So yeah, this is the topic, the main idea. And so the model that this time I'm going to use is the new couple ocean atmosphere simulation run by Dimitris and Andrea Molot. Because something that we found is that, well, it also, the kinetic energy fluxes computed from models depend if you're using a coupled one or uncoupled simulation, as I'm going to show in the next slide, for in the coming slides. So yeah, so the region I'm going to choose is the Kuroshio extension, which we know that is a highly energetic western boundary current with a lot of mesoscales, with a lot of submesoscale, and also the submesoscale follow the seasonal variability. So Now going to the frequency and web number space for models, we learned that the nonlinear interactions are located in this part of the spectrum, where the kinetic energy is distributed continuously across the web number and the frequency, and also that from here you can identify the which scales, spatial or temporal scales, are the mesoscale located, also mesoscale are defined. But here a more interesting information is that, just following Brian Arvik's paper, that where he showed that the kinetic energy fluxes are not only occurs in space, but also it happens in time. And now, from looking at this frequency web number space, we know that these nonlinear interactions follow the Taylor approximations, the non-dispersive line here, where the web number is directly related to the frequency. So in order to have a satellite based measurements useful for this type of analysis, the temporal resolution and the spatial resolution has to be somehow dynamically consistent in such a way that the combination of the spatial resolution and temporal resolution has to be close to the Taylor approximations. So that's why Topes Poseidon, well, somehow it was useful, because you have this temporal sampling, which is kind of consistent with the spatial resolution. Now, you think in SWOT, well, except the fast sampling phase, the SWOT increases the spatial resolution, although the temporal sampling is not as good as, or it can be some, we're gonna be a hard time getting the interpretation of the kinetic energy fluxes. Why? Because except for the fast sampling phase, the temporal sampling is not it can be not appropriate. So this is something that we have to think about, and once we have the data. But during the fast sampling phase, I think we had a golden opportunity to assess this, to confirm what I'm just saying. Now, in terms of ODYSEA, so the present design that Alex and Nestor and the team has in mind, so now we know that we can, in terms of surface currents, we can go down to 10 kilometers, but also in some places like mid-latitudes, like in the Kuroshi extension, we can have almost two observations per day. So we can fill up all this gap. And as you can see, well, is the temporal, the combination of the spatial resolution and temporal sampling is somehow not optimal for the computation of the kinetic energy fluxes. So this is an idea that we have in mind, and we are trying to understand if this is true. If to have an optimal satellite-based measurements, the resolution in space and in time has to follow the Taylor approximation. So this is a study that we are conducting. Now, just to summarize a little bit. So from altimeter, from conventional altimeter, we can compute the kinetic energy fluxes, but only the geostrophic one. We can get the geostrophic currents, and then we can compute the nonlinear terms in the kinetic energy equation. Now with ODYSEA, we have the total surface currents, the geostrophic plus the ageostrophic component. And from numerical models, we know that the ageostrophic component is the one in charge to drive the direct kinetic energy cascade. Plus we have the wind stress. So we have kind of extending the terms in the, well, we are able to resolve most terms in the kinetic energy equation. So this is an opportunity to address the kinetic energy fluxes across the interface, but also how the kinetic energy is distributed across oceanic motions. So this is the topic today. Is I'm going to focus in this term here, and so the next results are how to say. Well, the next result as just are meant to support the ODYSEA science objective number 2. which is a focus on the ocean scale interactions. And the idea first is to identify, well, the effective resolution of ODYSEA, whether the temporal sampling is good enough, and if the ODYSEA is able to capture the dual kinetic energy cascade plus the seasonality of the small scale motions. So first, the task was to choose the numerical model. And again, GPA, we have these two options. One is a couple simulation. This is the bottom one, and the well-known LLC simulation, which is a uncoupled simulation. And here I'm showing the annual kinetic energy and the Kuroshio extension and the Kuroshio current. And as you can see, there is, I mean, by eye, you can see a big difference. And this difference lies in the mean flow, how strong the mean flow and how coherent is the mean flow in the coupled simulation when you compare to the LLC. Of course, this difference has an implication in the kinetic energy fluxes, because now you have a stronger mean flow in such a way that it can trigger the production of more mesoscaleres, either more mesoscaleres or either a stronger mesoscaleres. And this has emphasized in the kinetic energy fluxes. So I computed the nonlinear kinetic energy fluxes during 1 year. So the top panel is from the coupled simulation, and the bottom one is from the coupled simulation. So you can see here is emphasized how the inverse kinetic energy cascade but it's huge discrepancies at inverse kinetic energy cascade. The direct cascade it remains about the same. Also, the injection scale remains the same, but what changes is the inverse kinetic energy cascade. So which one is the correct? I think that's the an opportunity for ODYSEA, because if you compare one model against the other, is different. Even here, the type of model is the same, but one is coupled and the other one is uncoupled, and even that you have a big discrepancy. So I think ODYSEA has the opportunity to fill or to give an answer about these discrepancies between models. Now you compare observations against model. Well, maybe not correct, although because in situ measurements are very localized, and this kinetic energy flux analysis depends on the size of the domain. The domain has to be large enough to capture mesoscaleres, but not too large to lose local dynamics. But it's not that simple to compare models against observations. But yeah, so here and after, the results are going to be based on the coupled simulation. And let's see how it goes. So I'm going to use the ODYSEA simulator developed by Alex Weintier. And just that we are trying to mimic how ODYSEA will observe. So I'm using, one of the capabilities of the ODYSEA is, one of the characteristics for ODYSEA is the 5 kilometers footprint, the almost twice a day observations of mid-latitudes, which are important for this analysis. And here's an example of the combination of the ODYSEA simulator plus the coupled simulation. So remember that the white swat of ODYSEA is about 1,600 kilometers. Here for this analysis, I'm going to use the requirement error. Sorry, this is not base. This is the requirement error of 50 centimeters per second, which is conservative. 50 centimeters per second. Now we know that thanks to Alex that the expected performance is way much better than 50 centimeters per second in terms of the random error. And one of the science requirements is to identify the optimal combination of temporal aberration and the spatial smoothing in such a way that we can have an effective resolution of 30 kilometers wavelength. So this panel is just to show how the ODYSEA simulator operates. So here we have the nature run. Let's say nature run. This is the coupled simulation. Then you have the ODYSEA sampling. And at the end, we have the ODYSEA with the random noise added. Remember, I'm using the 50 centimeters per second. And so first is identify the best combination of temporal sampling and temporal averaging in order to retrieve the 30 kilometers effective resolution. For the left panel I'm showing the web number spectrum of the kinetic energy. The blue line is the nature one, is the coupled simulation. The orange line is ODYSEA without noise. They're just considering the spatial sampling of 5 kilometer footprint. And the error, the 50 centimeters random noise is in the green line. So, and the red line is when you combine the ODYSEA sampling plus the error noise. So without any temporal average or any spatial smoothing, the signal to noise ratio equal to 1 is about 80 kilometers in terms of wavelengths. So yeah, this is not a good, but remember this is the 15 centimeters per second. Now I did a several analysis, and what we found is that if you use a 3-day average and 10 kilometers smoothing, you can get the 3 kilometers effective resolutions in terms of wavelength. So this is the right panel here. This is when you take into account the temporal average and the spatial smoothing. And so here, okay. So now the question, okay, this 30 kilometers is sufficient to capture the seasonality with small scale motions. Okay, let's see. So first, here I'm going to emphasize the how it looks like the data in the physical space in here, because I'm going to emphasize that, well, now we have a wide SWOT in such a way that we can have the curvature of the flow. And so we have the geometry of the flow, that we know that the curvature of the flow is important to drive or to trigger some instabilities in the ocean. So now here, so the left panel is just the ODYSEA without the noise, and the right panel is ODYSEA plus the noise. And here and after, I'm going to focus in this region here and see if the seasonality of the small scale kinetic energy shows up in the ODYSEA performance. So yeah, so here it is. So I took this small box and I compute the kinetic energy spectrum each ODYSEA sampling or ODYSEA SWOT, and for 1 year. And I'm focused, and here I'm showing just the kinetic energy level containing between 30 and 100 kilometers band, which is the band that Sasaki and Era defined it to as small scales. And so here I'm using the 3 days average and the 10 kilometers smoothing. But as you can see, even at even considering this temporal sampling and the spatial smoothing, we were able to retrieve the seasonality of these type of motions, maximum during the winter and the spring, and minimum in the summer and late fall. And the differences between the two, the orange line and the blue line is in the bottom panel. As you can see, is almost fairly the same. It doesn't vary much. I mean, it doesn't follow a seasonality, which means that, okay, there is not such some artifact in our estimation. So yeah, ODYSEA, even at this, considering the 50 centimeters per second as a random noise, and after the temporal average and the spatial smoothing, even though ODYSEA sampling is able to retrieve the seasonality of the small scales, which from numerical models, we know that this is associated to this seasonality, there is this nonlinear or this dual kinetic energy cascade. So let's see if ODYSEA is able to capture the inverse and the direct cascades. So first, here I'm showing the kinetic energy fluxes without any spatial smoothing and no temporal average. So just considering the 5 kilometers footprint and the random noise. So the blue line is without the noise. This ODYSEA sampling without the noise, and the orange line is ODYSEA sampling plus the random error. So as you can see, the random noise have an impact on either in the inverse cascade or in the forward cascade. Although in the inverse cascade, you can, I mean, you can define that it is a consistent or systematic negative sign. So there is no, you can identify or you can work on the inverse cascade. However, the one that is much impacted is the direct cascade. Well, it makes sense because the small scale motions has a relative weak speed in such a way that the random errors can have have an impact on it. Although the injection scale is about the same, it doesn't change. And now, okay, how to mitigate the impact of the random error in this estimation. Again, I'm going to use the 3-day average and the 10 kilometers smoothing, but keeping the 50 centimeters per second. So now you can see the inverse cascade, it matches nicely with the ODYSEA without the noise. And now we were able to get this systematic positive sign in the forward energy cascade. A little bit underestimated. I think this is just because of 3 days we are killing the part of this high frequencies of mesoscale motion that we know that are highly ageostrophic. So here is a little bit underestimation. However, I need to add a little bit of statistics here or error bar just to see if there is a significant differences between the two. But yeah, even considering this 3-day average and this 10-kilometer smoothing, we get the dual kinetic energy cascade, inverse and forward cascade, as well as the injection scale. And so just to finalize, here is just a summary. And so with this, considering the 15 centimeters per second as a random noise, again, this is a very conservative random error. Now we know that the performance is way much better. But even though we were able to retrieve the seasonality or the small scales between 30 and 100 kilometer ranges, and also we fully captured the inverse cascade, and the forward cascade, well, is partially resolved because of this temporal average and the spatial smoothing of 10 kilometers. Because you combine these two, you are almost killing all the high frequency and motions associated some mesoscales that we know that are highly ageostrophic. And so this is one of my last slides. Now, recently, Drew Balwada and et al. They use a bunch of drifters to estimate the kinetic energy fluxes. And what they found is that, well, this is in the Gulf of Mexico, but they found that the injection scale, it goes all the way down to around 1 kilometer in the summer, and between 3 and 5 kilometers during the winter. So maybe the satellite data might not be sufficient to go all the way down to here. But we have Doppler-Scat. We have Doppler-Scat to fill the gap between the satellite and in situ in water measurements. And one of the lessons learned from ESMO experiments is that we can, and the Doppler-Scat is able to get this fine scale motions in the ocean and with huge relative vorticity and huge divergence, that we know that this type of motions are those ones that drive the direct cascade. And so in some future, it would be nice to have these two instruments working together in to fill the gap between satellites and in-water measurements, that in such a way that we can fully capture the ocean scale interactions. So this is my last slides, and that's it.
Thank you, Hector. This was amazing. Questions? So while people are thinking, I'll say first, the question I was going to ask you addressed in passing. Of course, the big question is, what's the uncertainty? And I guess it's on your to-do list.
Yeah, it's my to-do list, exactly. Yeah.
So that would be really interesting to see that.
Uncertainties in the kinetic energy fluxes, right?
Yeah.
Yeah, this is my to-do list.
So this looks fantastic. And if you can assign uncertainties to it in some form, that'll answer all the questions that people might have when you write it up. Tony has his hand up.
Thank you very much, Hector. So in this plot here, if you use 3 days and 10 kilometer smoothing, the orange and blue curve will be much closer, right? So now if you go back, that's right. If you go back to the previous slides, I wonder if you not to do 3-day averaging, that kind of kills some of the, reduce some of the immersed cascade energy at high wave number, but you use longer, you use more, another 3 months ensemble, another winter, for example. Let's say you use 3 of them for a 3-year mission. I wonder how, if that's going to do anything, or you only have 1 year simulation, right? That's a problem with the model simulation. So what I'm getting at is that if you have multiple winter realization and multiple basin, because the physics is similar, you know, in the mid-latitude North Pacific, mid-latitude North Atlantic, or even, you know, South Pacific and South Atlantic, for that matter, South Indian Ocean, they are similar. And if you take those basin average and multi-year average, so that gives you like, I don't know, 10, 12 realization. I wonder whether that will have the same effect of making the blue and orange curve similar, without killing the spectral energy flux at high wave number. But I realized that you only have 1 year of simulation, so that's I suppose you can do average of different basins, you know, mid-latitude North Pacific, Atlantic, but probably not in time because you don't have 3 years.
Yeah, we have 3. We have 2 winters. Well, we have 2 winters.
Yeah, in that case, it might be good to take a look at the orange curve and the blue curve for the other winter to see whether, you know, the orange curve may rise above the blue curve for another season, another year.
Yeah.
So
yeah, that's a good suggestion, Tony. Yep.
Thank you.
Shen has his hand up.
Hi, good morning. So I think you assumed that the noise was going to be random in space. And so I'm just wondering if you thought a little bit about what might happen if you actually had some spatial correlation in your wind. So if your spectrum of the noise had a little bit of a slope, how would that change the result, you think?
Oh, you mean if the wind have some also, because, well, we know that the random error depends on the wind speed, right? Is what you are kind of thinking, right?
I don't know. So you had a wave number spectrum and you had the noise being just white, right? So I was just wondering, you know, and because you're trying to look at, you know, spatial gradient and everything. So I was just wondering if you had just a little bit of a slope in that spatial noise. I'm just wondering, you know, would it be, maybe it could help you for the forward cascade? And I don't know. I'm just wondering what would be the implications of that.
Oh, you have a slope. Okay, let me see.
And do you think it's a good assumption that the noise is going to be spatially random?
Especially,
well, may I comment on that?
Yep.
Yeah, so I think Alex Weintier and Ernesto Rodriguez can provide a much better comment on this. So the correlated error we'll try to minimize the correlated error in the retrieval. And so that's one thing. And the second thing is that we need more ODYSEA results. Let's say in the next year or so, if we advance into the step 2 proposal, we definitely need to simulate the impact of with some assumed correlated error to see how it may impact our various science objective.
Yeah, so if
That's
I
a good
could
point, Shay.
add a little bit, I think it's an excellent question by Shane, and it's something that is going to be one of the dominant long wavelength errors or long and to medium wavelength errors, errors that are correlated with either the wind changes, the wave changes, or changes in the attitude. Those don't, they're very small compared to the 50 centimeters that Hector was talking about, but in spectral space, at longer wavelengths, they can be significant, especially when you're taking the derivatives. So a large part of the mission concentrates on improving those errors through either improvement of the geophysical model function or through a better estimation of the and characterization of the pointing of the spacecraft, which is the dominant long wavelength error that we need to talk about, and is not included in this 50 centimeter per second. On the other hand, when you look at the spectrum of those things, the total RSS is much smaller than 50 centimeters per second. So you really, in order to get a full assessment, you really have to go to the more realistic estimates of the errors, which are more like half of that, plus some additional long wavelength errors. But I think it's an excellent open question.
Great.
Right, Ernesto made a very good point that 50 centimeter per second is not the performance of the instrument. Yeah, it's a requirement from the science and application objectives, and the actual performance is more like half of that, or 60% there.
Eric Desaro has his hand up.
Yeah, hi. Nice talk. Hi. It's striking the difference between the nonlinear transfer in the coupled model and the uncoupled model. And I'm wondering, either from you or anybody else, if we understand why that is. And there's a bunch of other related questions, like what about the, so there's obviously there's the ageostrophic motion that's associated with the wind. There's also essentially what scale of the wind affects what scale. There's a bunch of other transfers which have to do with putting the wind field in here. And I'm not actually sure what all the things you can compute are, but it seems like, given you have that, in other words, you could say, I'm only gonna look at the low wave number or low frequency wind, or the high frequency and the high frequency wind. There's a whole bunch of other things like that are extractable from this data. And I'm wondering if we even know anything about that physics.
Yeah, I think, well, one of the things that I have learned is, yeah, the high frequency winds in the coupled simulation, what is higher than the uncoupled one. And this high frequency triggers another type of motions in the ocean that either are near inertial waves that interact with the submesoscales.
Yep.
That's one. Two, if the winds, it gets stronger and aligned to the front, it's also another type of instability that enhances small scales. Two, and second, here, well, actually, I'm not sure how to explain why the mean flow in the coupled mode is more coherent. That's a question that we are trying to answer. But so yeah, at least at the high frequency motion in the small scales, I think I have this notion, and I computed that the Ekman buoyancy fluxes are larger in the coupled simulation. Then the high frequency motion that in the wind that trigger near inertial waves in the ocean interact with submesoscale fronts, also enhances the small scale activity in the ocean. That's two. And what else? And yeah, at least these two that I really know what's happening. Eric, what happened at why the mean flow is more coherent? I think that maybe another more experienced guy like Brian or Dimitri, I don't know what they call. Brian, yep.
Hi, Hector. Yeah, not really nice talk, and sorry I interrupted you early. I was just very excited. One thing I'm curious about is how, maybe you mentioned it and I missed it, is how you calculate your derivatives. Are you doing them spectrally or by centered difference?
As in the spectral domain.
So I guess another thing I wanted to bring up is I've played around a little bit with the ODYSEA simulator stuff that Alex provided. You know, I did a simple calculation and you know, the with and without noise results are fairly different, as you know. Have you thought about using noise suppressing differentiators? Maybe it's something we could talk about offline if you're interested, but there's the applied math community has this whole class of differentiators that kind of give the larger scales and get rid of the small scale noise.
Oh.
It might be worth trying that out just to see.
Yeah.
And Brian, that's just effectively combining the filter that you might use with the differentiator in an optimal way, right?
Okay.
I think so, yeah. I mean, it's just, yeah, there's techniques in the applied math community for taking derivatives of fields that have noise in them. I mean, in a way, it's kind of like doing, I think essentially what they do is they just do a polynomial fit through the larger scales, and then we know how to differentiate polynomials. But yeah, I'm just thinking about that because the noise in the simulated data is really big, and you can see in one of Hector's plots that it's not only big, but it's at small, yeah, that one there. It's at small scales, so it's going to be really enhanced in the derivatives. So how you take the derivatives probably matters.
Yes, of course. Yep.
That's a great point.
Brian, for the ESMO data, we've been using Lowe's, basically weighted Lowe's estimation, which does exactly that, and it's significantly better than just taking finite differences and smoothing.
Okay, so you have thought about that in that case. Yeah. Cool. So maybe I'm suggesting Hector might want to try that in these calculations.
Yep.
Because, you know, I think for the spectral flux, it really matters because it's a triple product, right? You have a whole bunch of derivatives.
Exactly. Yeah. Yeah.
Thanks.
Thanks, Brian.
Yeah, thanks.
Hector, I have a question. I'm looking at your coupled versus uncoupled. I'm thinking that for heat fluxes, Reese Parfit did some stuff, and probably Tony worked on this too for the butterfly proposal, where the atmospheric forcing and the ocean response were offset in time. And I'm wondering how much the coupled effect depends on the fact that these are really precisely at the same time. And if you offset the wind and the current in some way, we did. Maybe that's not possible in these outputs, but
well, we have the models, the model opals to view offline the heat fluxes. We have them, and we can well, this is for butterfly, but yeah, I think we can do it. This offsetting with the wind speed and the temperature, for instance.
Yeah,
this can be done.
So, and the other thing I really wanted to ask is, one of the big things that ODYSEA will deliver that we haven't had from altimetry is total current versus geostrophic. What would these quantities look like if you only pulled out the geostrophic component? Have you played with that at all?
Yeah, I think if we go back, well, I haven't done is ongoing. that type of calculation, just getting the geostrophic and then computing the kinetic energy fluxes. One thing you can get is like in the geostrophic approximation, here is going to be 0, and of course it's going to be also 0 in the direct cascade. And on the other hand, if you take into account only the ageostrophic component, you are going to get the forward energy cascade. So that's one of the advantage of ODYSEA, that, well, we think that we can have a more healthy direct energy cascade compared with SWOT and conventional altimeters, of course. So yeah, this is one of the analysis that's also in my list.
Great. Tony has his hand up.
Tony, yep.
Yeah, along the same question, has anybody done this kind of calculation in the equatorial ocean, say near the Kotang tropical instability wave area, where there are also some mesoscale variability? And I'm not familiar with the literature. So do we know how that curve may look in the Kotang area, for example? If not, might be a good thing to look at. And that will make a difference whether you use geostrophy assumption, versus the total surface current.
Yeah, I mean, Scott and Wong's calculation used the geostrophic assumption, so I don't have it in front of me, but I doubt that they did anything on the equator because
Yeah, no,
Mhm.
not at the, yeah.
Mhm.
Thanks, Brian.
Yeah, it's an opportunity.
Yep.
Any other questions? If not, we'll wrap up. This has been a really great talk, a really great discussion, and thank you, Hector, for doing this.
Thanks for the feedback, guys. Appreciate it.
Thank you, Hector.